Okay, so this is just conceptual review. Okay, so shout it out. Stronger the acid, the blank the conjugate base.
Weaker.
Weaker. Why?
Because it's a better acid.
Go backward.
Okay, so the weaker the conjugate base because it's going to go reverse and reform. No, that means it would want. That means it would be a really strong base and it would react fully in the reverse direction. So it's going to fully go forward and never go backwards, meaning it will not re-react. Larger the Ka value, the blank the acid. Why does that make sense mathematically? Okay, but if it dissociates more, why does it mathematically make sense? So what am I asking for? Right, so the concentration of the products versus the concentration of the reactants. Remember, that's how you set up a K, yeah? Okay, little k for kinetics is different than K for equilibrium. Why can't we choose a different letter? Don't know. So the number on top is bigger, meaning the K is stronger, or is larger, meaning we have more acid forming, or H plus is forming. The larger the concentration of OH, the lower, because it's meaning it's more basic. So then what about the pH? Okay, so everything's gonna, you gotta think about the inversely related stuff. The more concentrated the weak acid, this is a random fact you had to know. The more, the more concentrated, yeah, the more concentrated is the lower. I was thinking it's a more dilute. Because in our examples we had a regular acid, maybe 1 molar, and then another acid, the same acid at maybe 0.1 molar. 0.1 molar dissociated more due to Le Chatelier's principle. These are just predictions, no actual calculations. I'm trying to just get your brain warmed up here. Predict the pH. First of all, identify a salt, acid, or base, and then predict the pH. Ready?
Salt.
Okay.
7.
Why pH 7?
Because it comes from KOH, which is a strong base, and HNO3, which is strong acid.
Okay, so parents are strong acid and strong base from the KOH and the nitric acid. Good. 7. Next one. Acid. So
It's going to be less than 7.
it's a weak acid, so it's less than 7. This one.
That is great.
Okay, I heard salt,
So that's a salt, because calcium hydroxide,
calcium hydroxide, and
hydrochloric acid.
hydrofluoric acid.
So it's basic.
Calcium hydroxide is a strong base. Hydrofluoric acid is a weak acid, so that's going to be more basic. You're remembering a little bit here, okay?
Yeah.
And this next one,
Base.
definitely a base. It's going to be lower. Greater than 7. Ammonium bromide. Sounds weird.
No,
Why?
it's a salt.
Okay, I heard a salt, but it's an acidic salt because why?
H2O is a
Right.
strong acid, NH4OH is weak base.
Right. So ammonium hydroxide is a weak base. Hydrofluoric acid is a strong acid. And what was the acidic? Next one.
Base.
Right. Ammonia is just a base, but it's a weak base, but it's still greater than 7. So these are the types of questions we did before break. We did basically the pH of salts, acids, and bases, and you did all your predictions, and you actually did calculate the pHs. How would you find the pH of, and these you just can tell me how you would find the pH of versus us doing this as an old quiz. I just want to use it for review. Whenever we see the smart board do random things. Oh, I accidentally went backwards. There it is. Whenever we see this thing, identify it first, acid, base, or salt. Okay, so then strong acid, weak acid. So how do you find the pH? That's only for strong acids. You can directly take the concentration, assume it's H+. We have to do what? So we have to set up an icebox with a Ka value, solve for X, plug in X to the negative log of H+, and get the pH. Okay, do we remember that? You have to set up an icebox. Okay, so I'm just going to put ice here and Ka. Sometimes it's easier just to think about your process, because if you know your process, you can do a million problems, but we're not trying to do a million problems. Next thing. It is a salt, but then how do you find the pH?
It's basic, because NaOH is a strong base.
So that's your prediction, but then if I actually want to find the pH. We know it's a basic salt. Anybody? Which one's going to be added to water? Which one's the important ion? Right, because sodium added to water is going to make sodium hydroxide. It's going to go 100% back and not do anything, no reaction. Cn minus plus water equilibrates to cyanic acid and okay, so definitely showing again doubly proving right. We have nu as a basic salt from prediction. We can see it's making hydroxide, so it's definitely basic. But then what do you have to do?
find the pH from the K
So this is the conjugate base of cyanic acid, right? So we have a Ka value, like in a textbook someplace, for a cyanic acid. What is this doing? Acting as an acid or as a base? Because it's making hydroxide, and what is it doing? Right, it's definitely accepting H plus from water. So this is acting as a base. This is acting as an acid. So this is your whole, like, you're trying to remember your definitions. This is Bronsted-Lowry base, making cyanic acid. So if you're acting as a base, you must find the Kb from the Ka. And how do you do that?
1 times 10 to the 14th over
Okay.
the Kw over K.
Right. So if you remember, Kw equals Ka times Kb. That's your initial equation. And if you're looking for the Kb from something that's normally an acid, you have to implement the Kw constant to find the other thing. So then once I find the Kb, I can set up an icebox where I have the reactant concentration of 1.25 molar minus x, x, and x, solve for x, find the POH, and find the pH. Do you remember that a little bit?
Yeah.
Okay, I'm just trying to get some highlights here. Next one down here, number 4. Acid, base, or salt, number 4. It is aniline, actually. Aniline looks like this. It's a base. Oops. NH2 on the top. This is like a hexacycle, like a benzene ring kind of. The NH2 up here is supposed to kind of resemble ammonia. And you know ammonia is a base. If you can remember that, you should be able to remember it's a weak base. And it readily accepts H pluses to make NH3 plus on the end. Okay, so that's definitely a weak base. How do you find the pH of weak base?
So you do an icebox.
You have to do an icebox with the Kb, solve for x, find the POH, find the pH. Is this gibberish?
No.
How are we feeling? Okay, I got like 3 people going, yeah, I totally remember. Okay, last one down here, 6.
That's a strong acid, so it's just the
Yeah, just negative log. There you go. Strong acid, negative log. So you've got all these tools in your tool belt. You got to remember which ones are used for which thing. Okay. Let's go ahead and do a couple notes on polyprotic acids. I'll do 1 or 2 examples and let you guys practice on that one. It's not very different. It's just one extra step in your process. So polyprotic, diprotic acids, triprotic acids. This information itself is not in your notes, but some of the questions we're going to refer to are in your packet, and I'll tell you where they are. So anytime you have a polyprotic acid, it means that you have extra H pluses that are readily able to dissociate. So the very, very first one is going to dissociate the most. And that's because there's, nothing resisting or causing the resistance of the dissociation in the solution. There's not a bunch of H pluses already in the solution. It's just the acid dissociating. So I want you guys to write down the dissociation of sulfuric acid after you write down whatever else you need to. So when the first one dissociates, it's going to create a significant amount of H+. That's probably going to be the predominant dissociation that controls the pH. The rest of them don't dissociate quite as much because there's some ions already present in the solution, so due to Le Chatelier's principle kind of shifts back. So what's the very first deprotonization or dissociation of sulfuric acid? H2SO4. Good job, guys. Keep going. Plus water. H3O plus and HSO4 1 minus. Please put your charges. It's really important because you're just exchanging an H plus a proton, so it does change the charge. So this right here, I've written it as equilibrium. Is that true?
No.
No. Why is this one? This one's a special case. Why is that not equilibrium?
Because it's a strong acid.
It is a strong acid. There is no reversing. It's just straightforward. That one has a forward arrow only. This Ka value here is literally very large. You guys have your Ka value sheet I gave you last week, week before, last year, or whatever. It doesn't have It doesn't have a Ka value listed on it. On the very top, those are the 6 strong acids, and they don't have a value listed for sulfuric acid itself. But later on, it will. I actually don't know why it doesn't have another one here. I'm looking for something else, but I'll tell you guys the value. All right, so the Ka value for this one is just very large. The second dissociation is now taking that product here, the bisulfate ion, HSO4 1 minus, adding it to water. This one, is this a strong acid or weak acid? This one is what? Definitely is weak, right? It's actually amphoteric. It can gain a proton. It can donate a proton. We're making it act as an acid, so we have to make it donate. So what's it going to make? So hydronium and sulfate. 2 minus, good. So in this example here, this would be called the Ka2. So the Ka1 is what you denote for the first dissociation. Ka2 is what you denote for the second ionization. This is like 1.2 times 10 to the negative second, something like that. It's not very small, but it's small. And I have that someplace. That's it. There's no triprotic. There's not a third thing to take off. Yeah, 1.2 times 10 to the negative 2. So that's how you write it. If there's a third one, you would write a third BCE here. And so you can see the difference in the ion, or in the structure. You can see the OH or the H coming off, and you can see the second one coming off to make just straight up sulfate. This one technically really doesn't go back. It's only the first or the second one that goes back. So let's do an example and actually determine the pH. So we're going to use phosphoric acid, and we're going to take any ion that's made, and we're going to use it in sequential ice boxes if needed. So calculate the pH of 5.0 molar phosphoric acid at an equilibrium concentrations of blah, 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 blah. Okay, I give you all the K values. Very first thing you want to do is write out the first dissociation, and then we'll write the second one, and then we'll write the third one. The very first one is going to be phosphoric acid. Always add it to water for acids. For bases, weak bases, we do add it to water, but not all the time. Well, we include that for bases. So this goes to H2PO4 1 minus. If you were just trying to find the pH of the phosphoric acid, what would you do? No, this is weak. I can't do that. You just kind of told me how do you approach the pH of a weak acid? Have to do an ice box minus X. Good. So I'm going to take, and I'm just going to write ice right here. 5.0 minus X, X, and X. You see I'm just simplifying my ice box a little bit. It's nothing crazy. And then what do I want to do?
X squared over 5.0.
So Ka1, which is 7.5 times 10 to the negative third is equal to X squared over 5.0 minus X. And then I usually just put this next to it to say X is equal to hydronium, and then pH is equal to blah, blah, blah. So this is how I'm just kind of minimizing my work some. It's not totally minimized, but you know, I'm just starting doing ice boxes enough. You don't have to write out everything. So what are you probably going to do with X? Neglect it. So I'll write it here, and then I'll show my work afterwards. You know, is X neglectable when I do X over 5.0? I'll write that down in a second. So when you solve for X, you get 0.1936 molar. Okay? So I'm doing some of these calculations for you. This is what you're going to plug in for hydronium. And when you find the pH of just this right here, that presence of hydronium gives you 0.71 as your pH value, okay? Now, this X that you get is also representing the amount of biphosphate ion that's made as well, right? That is present in solution right now. So if that's present in solution, and when I do my second ionization, you'll notice I actually have 2 values present already. So this is our normal ice box, and then it is negligible. It's 3.87%. So, yep, totally can neglect there. So my second ionization, I'm going to have some stuff already present in I of ice. So my second one, I'm going to take that ion over there, and I'm going to ionize it, or allow for the protonization to occur. Deprotonization to occur, sorry. So H3O plus and HPO4 2 minus. This is Ka2 that's going to be representing this. But what do I already have present at the I for ice? What do I already have present?
Similarity of
So X, which is here, which is 0.1936. Do I have water? Nobody cares. Do I have hydronium? Yeah, it's X as well. So once these have dissociated, they're still in solution. Now this one's just undergoing further dissociation. So yeah, I already have this present as well. 0.1936. Do I have this present? No. So that's 0 at I for ice. So then once you undergo your changes for equilibrium, ICE there, what do you get here? You just do your normal thing, right? So subtract X, add X, and add X. So then when you set up your second dissociation constant, you set up the givens here. Ka2 is equal to 6.2 times 10 to the negative 8. 6.2 times 10 to the negative 8. And then you're just going to plug in your values that you have for your icebox. So 0.1936 plus X times X over 0.1936 minus X. What do you notice? How can you simplify? First of all, you probably are going to do what with X? Neglect, right? So you're probably going to neglect this X and this X down to 0, right? And then what do you notice? The numbers on top and bottom cancel, leaving you with X. So X is equal to Ka2. So X is equal to the hydronium concentration, because that's the part that's really relevant. We're looking for hydronium to get the pH, which is 6.2 times 10 to the negative 8th mole. Okay. This is also equal to, X is also equal, I'm sorry, this is not hydronium all the way. This is this guy. You have to add that to the X value original. That's what X is equal to, and we need the ion concentration, so I'm recording these as we go. But looking at the value of X here, I'm sorry, the 0.93, blah, 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 and the X value that we got, do you think that's going to change the pH very much? It's very insignificant. It's 10 to the negative 8th. It's not going to change the pH that much. So that's why I'm telling you the very first dissociation is probably going to be the one that determines your pH, because there's actually very, very little H plus made after that fact. Okay, so we only did this part really to get the HPO4 2 minus concentration. And then what do you think we're going to do? One more time. So HPO4 2 minus plus water equilibrates to what? So I heard hydronium and what? CO4, 3 minus, hallelujah, we don't have any more H's to get, right? So now what do I start with? What's my initial? This one has an initial, right? It's what we just calculated previously, 10 to the negative 8, good. Water, nobody cares. Hydronium has an initial as well. It's 2 that we've already gotten, so the 0.936 plus this, but that's not very significant. I don't think it changed it at all. Nope. So I'm just going to put 0.1936 here because it doesn't have a significant change. Do I have phosphate? Nope. So I'm going to go ahead and set up my ice, subtract X, add X, add X, and all this mess equals my Ka3 value, which is 4.8 times 10 to the negative 13th. 4.8 times 10 to the negative 13th is equal to X times 0.1936 over, plus X, over the 6.2 times 10 to the negative 8 minus X. And so when you go through and you try to neglect X, you can, I have it written down that all my little percentages, you just have to believe me there. Yeah, it's like X is equal to 1.537 times 10 to the negative 19th. Okay, a very, very, very tiny number. What is this equal to, though? What is this ion that we're talking about? So phosphate. So, oops. What other ions do I need to go ahead and identify the concentration of? Do I have them all? Yeah, and I did, and it's not significant. It doesn't even make a number, or change in the number. Huh? Yeah, the very first one. So that's kind of the point here. The very first one is the most significant H plus formation. Everything else makes a minimal change, so you can determine the pH from the first one. But there's one more ion that's always present when hydronium is present. We have to find the concentration of hydroxide, right? If hydronium's present, hydroxide's definitely present. So we have the concentration of hydronium, it's 0.1936. We have this guy down here someplace, the same as the hydronium. We have each sequential ion that's made, and then you have to find the hydroxide concentration. How would you do that? Okay, actually we can do it that way too. So 14, so pH, POH is 14 minus the 0.71 pH that we previously found, so it's about 13.29, and then we can find the OH concentration by doing 10 to the negative 13.29, and that would give us, I don't have it written down, it gives us a great number similar to that. Okay, so that would be our last ion concentration. Okay, so how new really is all that mess? It's just that different, same information, sequentially different. So how about you guys tell me? I'm gonna skip that one for now, because I found that once you do it twice, really you're okay. So this is your problem set. It's in your packet. I think this. Yeah, I have this one written down for you. So I'm trying to get done some of your homework. You're probably pretty problem set right now. So you guys start on this one, the carbonic acid, and then I'll go through how to do these setups with you. Because these are difficult, and I'll wait on them, but this is more conceptual practice. This is more exactly what we just did practice. It's on the bottom, right under salt hydrolysis, page 4. Thanks, page 4. And I'll tell you the Ka. Oh, actually, I got the Ka values right here for you. Doing question 1 right now, and I'll do the last full question. Shannon, do you need yours? You have yours? Can you pass up your packet? Can you pass it? we all get the pH from the first dissociation? Did you get 3.68? Okay. This is my like absolute minimized work. So as you start to kind of get through your ice boxes, you're gonna find your shortcuts. Don't get too shortcutty because then you'll forget why, like how to do it originally, or you'll forget why you're doing a shortcut. So my first ice box, I have x and x squared over 0.1 minus x. One a neglected x. Did you guys do neglect and check? What'd you get as your percentage? I got 0.2%. 0.2%. So anyway, less than 5, right? Whatever. It's less than 5. So our bicarbonate ion and our X are both 2.07 times 10 to the negative 4th molar. You immediately took that hydronium and plug it into pH, you get 3.68. Those two ion concentrations come down to your second dissociation. Minus X plus X and X. You'll remember again, if you ever have the same numbers on both sides, minus Xing on one side, minusing X on one side, plusing X on the other, those X's are neglected. And then you'll have the same number on top and bottom. So you might remember this in the future, but your Ka2 value is your X value for your next step. That X is carbonate. There's one more ion we've got to find. What is it? Hydroxide. So then you probably easily found hydroxide concentration by taking maybe Kw over the hydronium. So 1.0 times 10 to the negative 14th divided by hydronium of 2.07 times 10 to the negative 4th. And what'd you get for hydroxide? Thank you. 4.83 times 10 to the negative 11 molar. Huh? Yeah, me neither. Okay, so how do we feel about diprotic acids and triprotic acids, aka polyprotic acids? Feel okay? So I might ask again if we need to do another one after we go through the second set of your problem set. So I'm doing your homework with you right now, okay? Let's get this party started. The next set actually doesn't have any calculations. I'm going to have you guys set up work, but we're not actually going to calculate it. We're just going to set it up. All right, give me a thumbs up, smile, stand up and take a yoga break. I don't care what you got to do. You okay? I think I can finish this in less than 10 minutes here. Okay? Going down. Okay. So you'll see that all of these examples following have carbonate, bicarbonate, carbonic acid in it, right? So they're all definitely related to the first question. And I could ask for you to calculate every single one of these Ks by using the Ks given at the top, but we're just going to set them up and we can, calculate if we need to later. So the very first thing you have to realize is that I can put any of these ions with water, with another acid, with another base. Because, for example, bicarbonate ion is amphoteric, so it can react in multiple ways. So your job is to figure out how is it reacting? What the heck is it doing? Is it acting as an acid or is it acting as a base? Okay? So that my tip to you is look for water, see what that thing is doing with water, and then finalize your answer. So note to self, look at water to see how it's reacting, okay? So in this case, what is this doing with water? I want you to assign the word acid and base to either one of these reactants. So water is donating, right? Because you can see it's forming the bicarbonate. So this is acting as the acid, this is acting as the base. Okay, I can no longer talk Ka, I must talk Kb. But which one? Ka, is it Kb1 or Kb2? This is your choice. You have to look to see what's made. Well, the combination between these two are definitely regarding K1 or K2. K1 because it's the bicarbonate and it's the bicarbonate and the carbonic acid. It's not the second deprotonization to carbonate. So this is Kb1 from Ka1. Because I'm saying it's acting as the base, so I must talk about the Kb. It's the first dissociation, so I'm talking about Kb1. But how do I get Kb1 from Ka1?
It's Kw over K.
Kw over Ka1 is how I calculate the answer. You see, it's like a puzzle. You see how it's reacting with water. You assign it its role of acid or base. Since it's in the forward direction, there's no inversion, there's no like raised to the -1 or flipping the reaction. You just say, I must find the Kb from the Ka, but your choice is specific, it's K1 or K2. You okay with that? Student, can we do another one? So the answer to this would be Kb1, which would be, the calculation would be Ka or Kw over Ka1. And you could plug those values in and find it. Okay, next one. You guys tell me how I'm looking at this. I find
HCO3 minus acting as an acid.
Okay, hold on. I find water first, right?
Find
I'm
water.
gonna look for water real fast. I can see water here. I can see that carbonate's acting with water in the reverse direction, right? Okay. The reason I have to consider it with water is because every single dissociation is written, right, reacting with water. I have to see how it's reacting with water, and then from that perspective, I have to decide is it the reverse direction or the forward direction, meaning I have to flip the K's or not flip the K's. So I can see this reacting with water how? As a base or an acid?
Base.
Yes, so this is accepting again, so I'm just drawing my H plus being donated back. So the acid is water, and the base is the carbonate, right? Okay, so if I'm acting as a base, I have to find the KB from the Ka, correct? Am I finding Kb1 or Kb2? Because it's a combination of carbonate, the second deprotonated version, and bicarbonate, which is from the middle ground. So this is Kb2 from Ka2. But there's one more factor to consider. This is in the reverse direction, right? So not only do I have to find the Kb, but I also have to reverse the K value, or the reaction. So when I reverse a reaction, what do I do to K? Invert it, put 1 over K. So if I was just finding Kb from Ka, I would do Kw over Ka2, yeah, to find Kb2, okay? But I have to invert that, raise it to -1 power. Or just literally invert it by putting Ka2 over Kw. See confused spaces. Tell me what you're thinking, or tell me what's confusing right now. Got it? Who's got it? Who understands the process of doing this? Yeah, question? You good? Okay. So you guys do the next one, and then sequentially we'll kind of check as we go, okay? So I did one in the forward direction, I did one in the reverse direction. Actually, both mine are acting as bases, but you can, figure it out from here, I think. I'll check this one with you in a minute. You literally have to talk to yourself, though. Do you guys get to the next one? It's just straight Ka2. If you look at that, does that look like a normal dissociation? Yep, it's a ion reacting with water, making its whatever, but this ion is acting as an acid, so that's why we call it Ka. If it were the other way, if it were making carbonic acid again versus carbonate, it would have been Kb something. But that one's just straight up same dissociation we've always seen.
Why do you know that it's, I don't understand how you know that it's Ka2 or it's Ka.
You have to look at the combination of the ions or the things that relate to each other. So what I'm kind of zeroing in on are the bicarbonate and the carbonate species here. And since that's the second dissociation of the scheme of bicarbonate, of this, and this. Since it's this combination, that's Ka2. If it was this combination, it would be Ka1. So yeah, first you look and see how it's acting, acid or base. Second, you look for the combination of them. And then decide if it's reversed or not. All right, keep going. This is the rest of your problem set. another minute with you. When you're done, grab the phone book and put it in the top of your cart. I'll talk about it. Alright, I'm gonna check these in 1 minute. I'm gonna go ahead and grab Chromebook to get logging on. Good idea. And grab the paper on top as well. And another like bagel or donut stick or whatever. Somebody.
Come on, guys, let's get up.
I'm trying to keep you sugar filled so your brain has the, the necessary stuff to work. Oh, and I will bring us a Keurig in 2 weeks. I bought my mom a new one, so she's giving me her old one for my class.
What are you bringing?
A Keurig.
A Keurig.
And you have to make it before class. We're not going to be like coffee shop during class. You have to make it before class. And if you would like to start, hassling somebody for K-Cups or whatever the brand it is, I will start us off. I made a deal with her. So if I buy you a new one, which I have, is that the one I just bought for my class? It's the one that got me. Versus having one home function. I'm here more, so. I was like, I'll use that at school more. Okay, let's check these quickly, my dears. Windows. Alright, tell me just your basic setup. I don't want to have a number on there if it's K, blah, 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 for the next couple, okay? Hold on, let me find them on my paper. We're on D, correct? Alright, what'd you guys get here? Anybody? K, what'd you get here?
1 over K8.
Thank you. 1 over KA2, or you could have written that as KA2 to the negative 1. Thumbs up if you got that one. I need to go over them. You've got to let me know. So I'll quickly go over this one. You look for water. You see water's on the product side, which means it's probably going to be reversed, people. We're going backwards. This one right here interacting with the bicarbonate, going back to the carbonate means that the bicarbonate is acting as the acid because it's donating it back. The water becomes hydronium, so it's acting as the base. So you have to discover that it's acting as the acid first, and then you're like, oh man, it's also reversed. So it's the 1 over Ka, but then the Ka that it's talking about is the one between the last species made and the middle one, which is 2, not 1. Next one, would you guys get?
Ka1 over Kw.
Ka1, hold on, I'm looking at the right one. K1 over Kw. So basically, you previously had Kw over Ka1, and it was reversed because water is a product again. So water being a product, interacting with this, happens in a Kb manner. Right, so water is the acid, this one's the base, and since it's the base, you're going to have to find the Kb of the Ka, and that combination between these two are Ka1 because they're the first deprotonization. And so to do that, you must use Kw to get there. 2 for 2? Okay. Next one, what'd you guys get? It's close to Kw, but not quite. It's 1 over Kw, good. 1 over Kw because it's the reverse of water dissociation. Right, water dissociating would mean making ions. This one's ions coming together to make water, so it's the reverse reaction. Next one,
Just Ka.
it's just Ka1. And if you look closely, and I know you're in your process of look for water, I see how it's reacting, blah, 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 blah. You look at that, you're like, hey, that's just a normal dissociation. It's acid plus water yields stuff and stuff, or hydronium. And that happens to be the first dissociation. The next one, what'd you guys get? H?
Kw over Ka2.
Good. Kw over Ka2, which means you're representing Kb2, right? So that's the Kw over Ka is Kb. So the way you did this one was you saw water was interacting with carbonate in a way that makes bicarbonate. So this is acting as the base because it's accepting. This is acting as the acid. So if you realize that carbonate is acting as a base, you must find the Kb of it. But the combination of them is the second dissociation. Why did I write Kw over? Oh, it's Kb. Sorry, I was thinking I reversed it. And then the last one would just put right. So 1 over Ka1. Oops. Or you could put Ka1 to the -1. It represents the same thing. And if you look, you'll see that the Ka1, so the carbonic acid, interacts with water to make hydronium in the reverse direction. So that's why we're reversing it. This is acting as the acid. This is acting as the base. I saw a lot of you guys drawing your arrows and labeling them. That's your best process, okay? So don't just stare at it. Actually, a process. Okay, so we have about 30 minutes left in class. You guys grab the diprotic acid paper? Yes? Okay. This is kind of your introduction back again to titrations. We've already done a million titrations, but we have to start recognizing different spots on the graph. A graph can tell you like 10 different things, but you have to know where to look. So on this dry lab, I did it as a dry lab. There's a wet lab, meaning in the back versus on the computer, so that you would get it done in class. Okay, so that's my goals. You're going to be graphing this on an Excel file. If you would like for me to print it for you, you've got to send it to me ASAP. I'll get it printed during class if I can for you. I'll run to the printer and grab it. If not, you can sketch it, but you really need a good graph, so I prefer you to print it, okay? So on here, I'll go back to this other stuff. Oh, there it is. You must use an Excel. You must have a printout of your graph because it's very different than a normal titration curve, okay? Other than that, we have some key points to look at in the questions, but I don't really think I need to help you at all. You can work with a partner, but you guys can talk about it. I want everybody to manipulate on Excel. Some of us still don't know how to graph on Excel. Okay? You got data points, and I put this on my website. If I will put it on my website unless you want to just hand type your data points in, okay? Any questions? 30 minutes, break.